Okay guys, we're here in chapter 23, and at the end of the last video we were looking at a plane of charge. So just to kind of remind you where you're at, what we did is we took the plane and we broke it up into discs, and those discs, okay, we integrated over the rings. And then you integrate from the center, smaller rings, up to larger and larger rings. Okay? And as we integrate to larger and larger rings, what we create is a plane. Now, let me get one of my handy dandy things here. So when we integrate for our plane, okay, we get E out perpendicular from the plane to have a strength of K times Q, the amount of charge on the plane, times Z, that's the distance from the plane, divided by Z squared plus R squared to the 3/2 power. Z is our distance from the plane, R is the radius of the disc. Okay? Now, if we write it in terms of epsilon 0, we get Q times Z over 4 pi epsilon 0 Z squared plus R squared to the 3/2 power. Now, notice that when Z is 0, the strength of the electric field goes to 0, because we're essentially in the plane. Okay? And if R approaches infinity, as we have an infinite plane of charge, when R goes to infinity, okay, it's going to affect things. So think about R going to infinity. Well, that's for one ring. We add them all up into the disk. Okay? And we talk about the surface charge density, eta being Q over A. Then if we add up all the little rings to make a disk, E equals eta over 2 epsilon 0, 1 minus Z over Z squared plus R squared. Now as R approaches infinity, then Z over infinity becomes 0, and all of this disappears. And for an infinite plane of charge, then, we get the magnitude of the field is equal to eta over 2 epsilon 0. Now notice that there's no Z in here. No matter how close or how far you get from the plane, okay, the strength of the electric field is going to be the same if you have an infinite plane of charge. Now we know in reality we can't get an infinite plane of charge, but if we're in close to the surface of the plane and we're at the center of our disk of charge, then it approximates an infinite plane of charge. Okay? So we're going to look at problem 18 on page 654. So let's flip over. To the document you can, and let's look at problem 18. You're done? No. You go ahead and set up around me. You can set up around me. Okay guys, let's look at problem 18. It says a 20 centimeter by 20 centimeter horizontal metal electrode is uniformly charged to 80 nanocoulombs. What is the electric field strength 2 centimeters above the electrode? Okay, so let's scoot on over here. All right, now we have an electrode that's 20 centimeters by 20 centimeters, so that's 0.20 meters by 0.20 meters. So the area is going to be 0.2 times 0.2. So 0.2 times 0.2 is 0.04 meters squared. And it says the charge Q is 80 nanocoulombs. So that's 8.0 times 10 to the minus 8 coulombs. So eta is 8.0 times 10 to the minus 8 coulombs divided by 0.04 meters squared. So that's 2.0 times 10 to the minus 6 coulombs per meter squared. Okay? And the strength of the electric field is equal to eta over 2 epsilon 0. So it's going to be 2.0 times 10 to the minus 6 coulombs per meter squared divided by 2 times eta. And eta is one of those numbers that I don't have memorized. Okay? But if we flip to the back of the book, the value of eta should be here. Let's see, it must be in front of the book. Yeah. The value of eta is given to us. Pull this up. If you look at it, epsilon 0 is 8.85 times 10 to the minus 12. So it's 8.85 times 10 to the minus 12, and it has units of coulombs squared times newtons over meters squared. So notice we're going to end up with units of coulombs per newton. Okay? And if we do the division here, I have 2 exp 6 negative divided by 2 divided by 8.85 exp 12 negative, and I come up with 1.13 times 10 to the 5 coulombs per newton as the strength of the electric field at that location. Okay? Not bad, right? You should be able to handle that. Now, let's move on. Let's think about having 2 plates of charge. 2 plates of charge are very common. Okay? When we have 2 plates of charge, we're looking at a parallel plate capacitor. Okay, so 2 plates of charge. Now, each one of these plates is going to have the same area, and they're going to have the same magnitude of charge on them. In a parallel plate capacitor, one has a charge of plus Q, the other one has a charge of minus Q. They're separated by a distance D. Now, let's look at what the electric field is going to look like inside and outside the parallel plate capacitor. If we look outside the parallel plate capacitor, over here outside the positive plate, the electric field from the negative plate is going to point toward the negative plate. Okay? The electric field from the positive plate points away from it. Since these have the same magnitude of charge, the strength of these 2 electric fields, the one caused by the negative plate and positive plate, have to be equal to each other in magnitude. They're pointing in opposite directions. So they come together, they add together to give us a net electric field of 0. Same thing happens over here. They add together to give us a net electric field of 0. But inside, between the 2 plates, The electric field from the positive plate points away from it. The electric field from the negative plate points toward the negative plate. So those two electric fields are actually pointing in the same direction. They give us a net electric field that's twice the electric field of either one of them by themselves. Okay? So when you add up the electric fields inside the parallel plate capacitor, the strength of the electric field equals eta divided by epsilon 0. And the field points from the positive plate toward the negative plate. So a positive test charge in between the plates of a parallel plate capacitor moves in the direction of the electric field vectors. So it's going to move from the positive plate toward the negative plate, or experience a force from positive plate to negative plate. If we released it from 0, it moved from positive plate toward the negative plate. A negative test charge experiences a force from the negative plate toward the positive plate, the opposite direction of the electric field. And if it was released from rest, it would move toward the positive plate. So, always remember a positive test charge experiences a force in the same direction of the electric field. A negative test charge experiences one in the opposite direction. Now, inside the parallel plate capacitor, we have a very interesting electric field. It's called the uniform electric field because the strength and the direction of the electric field is everywhere the same in that region of space. We're going to look at two problems that has us calculating the electric field inside a parallel plate capacitor. Okay, we're going to look at problem 22. We're going to look at problem 24. Okay, remembering that the electric field strength inside a parallel plate capacitor is equal to eta over epsilon 0. Okay, so let's look at problem 22. Sorry guys, I have to walk back and forth, but we'll get through it. All right, we look at problem 2. It says two circular discs spaced 0.50 millimeters apart form a parallel plate capacitor. Transferring 3.0 times 10 to the 9 electrons from one disk to the other causes the electric field strength to be 2.0 times 10 to the 5 newtons per coulomb. What is the diameter of the disk? Okay, so we know that E equals epsilon 0, and we know the value of E here, magnitude-wise, is 2.0 times 10 to the 6 newtons per coulomb. And we know that we have 3.0 times 10 to the 9 electrons transferred. Okay, so our Q is going to be 3.0 times 10 to the 9 electrons, okay, times the magnitude of E, which is 1.60 times 10 to the minus 31 coulombs. Okay? Now, if you don't remember what E is, it's again one of those constants that is at the 10 to the minus 19. It's one of those constants that's in the front of your book. Okay? As my book slides. Okay, so constants. Then the front cover of your book. 10 to the minus 19. I was thinking about the mass of an electron. Okay, guys. front cover of your book. Okay? I have them underlined in mine because I use them so much. All right. Now, with this, I can get Q. So 3.0 EXP9 times 1.6 EXP19 negative. Okay. That gives me 4.80 times 10 to the minus 10 coulombs. So if I take E times epsilon 0, that should give me eta. So eta here is equal to 2.0 times 10 to the 6 newtons per coulomb times 8.85 times 10 to the minus 12 coulombs squared over newtons times meters squared. So the newtons and newtons divide out and one of the coulombs divide out. So eta 2exp6 times 8.85 exp12 negative gives me an eta of 1.77 times 10 to the minus 5 coulombs over meters squared. So eta also equals Q divided by A. So rewriting this, I have 1.77 times 10 to the minus 5 coulombs per meter squared is equal to 4.80 times 10 to the minus 10 coulombs divided by the area. Solving for the area, I get 2.71 times 10 to the minus 5 meters squared. So the area of a disk is pi r squared. So 2.71 times 10 to the minus 5 meters squared is equal to pi r squared. So r equals 2.94 times 10 to the minus 3 meters. The diameter would be twice that. So 5.88 times 10 to the minus 3 meters. So that's 5.88 millimeters. The question didn't tell us what unit it wanted it in, so you could have left it in meters, standard SI units, or if you'd written it out in millimeters, it would have been fine too. Okay? Now, the other question for us to look at would be problem 24. So let's look at problem 24. Okay, so look at problem 24. Right here. Let's look at it real quick. Okay. It says that air breaks down when the electric field strength reaches 3 times 10 to the 6 newtons per coulomb, causing a spark. A parallel plate capacitor is made from 2 4 centimeter by 4 centimeter electrodes. How many electrons must be transferred from one electrode to the other to create a spark between the 2 electrodes? Okay, so let's start working on it. Okay, guys. problem, what we've got is that we've got an electric field strength, E, in magnitude being equal to 3.0 times 10 to the 6 newtons per coulomb. Okay? And if I want to get the area of my electrode, it's going to be 4.0 times 10 to the minus 2 meters squared. Because it told us it was 4 centimeters per side. So 4 exp2 negative squared. So that's 1.6 times 10 to the minus 3 meters squared. And we're asked number of electrons transferred. So I need E, which is 1.60 times 10 to the minus 19 coulombs per electrode. Okay, magnitude of the charge. I know for electrode it's for an electron it's negative, but I'm just worried about the magnitude. And we know that E is equal to eta divided by epsilon 0, which is Q over A epsilon 0, because eta is Q over A. So 3.0 times 10 to the 6 newtons per coulomb is equal to Q over the area, which we got as 1.60 times 10 to the minus 3 meters squared, times epsilon 0, which is 8.85 times 10 to the minus 12, and it's coulomb squared over newtons times meters squared. Okay, and I'm going to solve for Q. We solve for Q. 3 exp6 times 1.6 exp3 negative times 8.85 exp12 negative gives me a charge of 4.248 times 10 to the minus 8 coulombs. Okay? And we know that Q is going to equal number of electrons times charge of an electron. Okay? And the magnitude there. So Q, which is 4.248 times 10 to the minus 8 coulombs, is going to equal our number of electrons times 1.60 times 10 to the minus 19 coulombs per electron, magnitude. Okay, so I divide through. .248 exp8 negative divided by 1.6 exp19 negative, and I get my number of electrons to be 2.66 times 10 to the 11. Okay, so those are two parallel plate capacitor problems. Now, okay, for a test charge in a uniform electric field, there of course is an electric force, and the electric force for a positive test charge is going to be in the direction of the electric field. For a negative test charge, it's going to be in the opposite direction of the electric field. So the force is equal to the electric field times Q test. So notice if it's positive, it points in the same direction as E. If it's negative, points in the opposite. And we know that force equals mass times acceleration. So if I combine these two, the acceleration is equal to E, the magnitude of the charge, the magnitude of the charge and its sign divided by its mass. Hi guys, I'm back. Sorry, I had to run out of the room real quick, but I'm back, I promise. Now, you haven't been gone, but I have, so let me just remind you. The force experienced by a test charge QT in a uniform electric field is equal, force is equal to the strength of the electric field times QT. Force equals mass times acceleration, so therefore acceleration is equal to the magnitude of the electric field times Q over M. And notice that if it's a positive test charge, the direction of the acceleration vector is going to be the same as the direction of the electric field vector. If I am dealing with a negative test charge, then the acceleration is going to be in the opposite direction. Okay? Now, in a uniform electric field, then, we're going to have a uniform or constant acceleration through that area. And we can talk about then how a particle is going to accelerate when it experiences an electric field. So let's look at problem 28. Then we may or may not look at problem 51 and 52. But if we don't do them, you guys are going to do them on your own. And then we're going to talk about a sphere of charge. Okay, guys, problem 28. It says an electron traveling parallel to uniform electric field increases its speed from 2.0 to times 10 to the 7 meters per second to 4.0 times 10 to the 7 meters per second over a distance of 1.2 centimeters. What is the strength of the electric field? Okay, so I'm going to start off by drawing a picture, and we're going to work from there. Okay, guys, so we have an electric field E like this, and we have an electron, and it's moving in this direction. Okay, it's moving in the opposite direction of the electron field. Now, its velocity initially, in fact, I'm going to draw this the other direction just so that the direction of travel is positive. So I'm going to draw my electric fields here, and the velocity of the electron in this direction. So velocity initially was 2.0 times 10 to the 7 meters per second. Velocity final is 4.0 times 10 to the 7 meters per second. So our acceleration is, let's see, and it does this over a delta x of 1.2 times 10 to the minus 2 meters. Okay? What we're asked here is the strength of the electric field. Now, remembering back, V final squared equals V initial squared plus 2ax delta x. So 4.0 times 10 to the 7 squared has to equal 2.0 times 10 to the 7 squared plus 2 times ax, and delta x is 1.2 times 10 to the minus 2 meters per second. meters, not meters per second. So let's figure out what A is. Didn't think these equations would slip up on you again, did you? So 4 exp7 squared minus 2 exp7 squared divided by 2 divided by 1.2 exp2 negative, I get an acceleration of 5.00 times 10 to the 16 meters per second squared. Remember, this is meters per second, this is meters per second, that's in meters, you'll end up with meters per second squared. So the acceleration equals E times QT over the mass. So I've got 5.00 times 10 to the 16 meters per second squared, and it's in the positive direction, has to equal E times 1.60 times 10 to the minus 19 coulombs over the mass, which is 9.11 times 10 to the minus 31 kilograms. Okay? So if we solve this for E, I have 5 exp16 times 9.11 exp31 negative divided by 1.60 exp19 negative, and get a value of 2.85 times 10 to the 5 newtons per coulomb. The kilogram meters over second squared, that's a newton, so we end up in newtons per coulomb. And since that was positive and this was negative, of course I would have gotten a negative value here, okay? But all we really wanted was a magnitude. So in my drawing, the electric field points in the negative direction, okay? But the magnitude of the electric field is 2.85 times 10 to the 5 newtons per coulomb. All right? Now, most of the problems in this chapter are pretty much plug and chug. I want you to do 51 and 52 on your own. We'll talk about it next time we have lab. Okay, guys. Now, let's talk about a sphere of charge. Okay, a sphere of charge is a charge that's not a point charge, whether it's a solid sphere or it's a hollow sphere. E, the electric field beyond the surface of the sphere, is equal to Q, the charge on the sphere, divided by 4 epsilon 0 r squared r hat. And r has to be greater than capital R, the radius of the sphere. Okay? When you look at problem 17. For a non-uniform, so it's a plug and chug problem. I'm not going to bore you with it since you're watching a video. Now, for a non-uniform electric field like the one that we see around a point charge, the motion of a test charge can be quite complicated. Because remember, the if we're looking at a, here, let me draw here. So if I've got a point charge here, okay, and let's say this is a positive point charge. If I were to draw electric field lines, okay, if I was at a point here, the electric field lines are closer together than if I'm at a point here, so I have different strengths of electric fields at point A and point B. So, you know, if I come in, if I am an electron moving through here, if I move, you know, if I'm headed on a trajectory like this, every place that I go as I'm moving, I'm experiencing a different strength electric field and a different force. So we don't want to look at every case here. What we want to look at is a very specific case for a charged particle entering a non-uniform electric field. Namely, we're going to concentrate in on circular pathway. So they stay a constant distance from the charged point mass, and they're moving around. Okay, let's go up. Okay? Now, if we're moving around a circular pathway around in this case, a source charge that's positive, and we're like a negative electron, harkening back to the Bohr model of the atom, then at this specific radius, this test charge is going to be experiencing a constant force, F on Q, okay? And it's a center-seeking force, so it's a centripetal force, okay? So all this force is going to do, because it's perpendicular to the velocity vector, is turn it. So at that constant distance from the source charge, the magnitude of E, the electric field, is constant, so the magnitude of the force is going to be constant, and the velocity, or the speed around that circular pathway, we have Q, the magnitude of the test charge, times E, the strength of the electric field, is equal to mv squared over r. Okay? So let's look at problem 58 on page 653. No, 58 problem. Okay. Problem. It says a 2 millimeter diameter glass sphere, okay, has a charge of 1 nanocoulomb. So Q, our source charge, is 1.0 times 10 to the minus 9 coulombs, and it's positive. What speed does an electron need to orbit the sphere 1 centimeter above the surface? So R, the diameter of the R, the radius of the sphere, is 1 millimeter, and little r, the distance from the center of the sphere to the electron, is 1 millimeter plus 1 millimeter, or 2 millimeters. Okay? So there's the pieces of information that we need, and we're asked V, the speed. Okay, so let's look at the equations that we've got. We look at the equations that we've got, we're going to use we're going to need Q test, which is 1.60 times 10 to the minus 19 coulombs. Okay, and we've got the equation Q test magnitude times E has to equal mv squared over r. Okay, now beyond that, we're also going to need our equation for a sphere of charge. We also need the E, okay, equals magnitude of Q over 4 pi epsilon 0 r squared r hat. So with all that, let's start plugging in. Okay. Now, first thing we need to do is get E. The charge was 1.0 times 10 to the minus 9 coulombs. 4 pi epsilon 0, 8.85 times 10 to the minus 12 coulombs squared over newtons times meters squared, times the radius here, which is 2.0 times 10 to the minus 3 meters squared. Don't worry about the r hat, we're not too hung up on the direction right now. So just getting the magnitude, I get 1.0 exp9 negative divided by 4 divided by pi divided by 8.85 exp12 negative divided by 2 exp3 negative squared, and I get, let me try that one more time, 2 exp3 negative squared times 8.85 exp12 negative times 4 times pi, 1 over that, times 1, yep. So I get the strength of my electric field to be 2.25 times 10 to the 6 newtons per coulomb. Okay? Now, we come up to our other equation. Our Q test is the charge of an electron, 6.0 times 10 to the minus 19 coulombs, times the strength of the electric field, 2.25 times 10 to the 6 newtons per coulomb. And that has to equal the mass of the electron, 9.11 times 10 to the minus 31 kilograms, times V squared over R, which is 2.00 times 10 to the minus 3 meters. So, solving for V, I have the 2.25 times 10 to the 6 newtons per coulomb times 1.60 exp19 negative times 2 exp3 negative divided by 9.11 exp3 131 negative, and then I take the square root of that, and I get the speed to be 2.81 times 10 to the 7 meters per second. Now, you could have also combined equations. If you combine equations, you would have had Q, the magnitude of Q times the magnitude of big Q over 4 pi epsilon 0 r squared is equal to mv squared over r, and notice that that would have divided out. You would have gotten this equation. You would have gotten v squared equals q times big Q over 4 pi epsilon 0 times m, and you could have solved it. Should come up with the same answer. Okay? All right. Now, we just need to talk then, to finish things up, about what a dipole does in a uniform electric field and what a dipole does in a non-uniform electric field. Okay, guys, a dipole dipole in a uniform electric field, all they do is they spin and align themselves with the field. So they do not accelerate. Okay? So let me draw a picture here. So let's say we have two plates here. This one's a positive plate. This one's a negative plate. So that the electric field vectors in here run like this. Okay, so these would be electric field lines. Now, if I have a dipole in here, okay, with a positive end and the negative end. The positive end is going to be attracted to the negative plate. The negative end is going to be attracted to the positive plate. So what this thing does is it'll rotate. Okay? And as soon as it gets aligned so that negative and positive is here, it stops moving. And it won't move back and forth because this end is experiencing a force in this direction, this end is experiencing force in this direction. Same magnitude of force, opposite directions, they cancel each other out and it sits still. So a dipole in a uniform electric field just rotates and then aligns and stays still. Now, when we put a dipole in a non-uniform electric field, then in this case, a non-uniform electric field from a positive test charge, it's going to orient itself first so that the negative end, of course, is pointing toward the positive test charge, and this is a little bit closer than this end. Because this end is a little bit closer than this end, there is going to be a net force on this dipole toward the positive source charge. And it'll experience a negative force and it'll migrate or move. Okay? Now we're not going to calculate it, we just wanted to talk about it. And that, guys, ends the chapter. So now you have all of chapter 23. So by the next time we meet, I'm going to start talking in chapter 24. You should have 23 and 22 done. Okay, guys? See you in class.